A switching modulator can also be used to generate a DSB-SC signal. So MFT is the message signal, and PFT is a rectangular pulse train. Both of them are put into a mixer in which they are multiplied in the time domain, producing V1 of t, and that is passed through a bandpass filter to keep the sidebands, producing V0 of t, which is the DSB-SC modulated signal. Alright, so let's do an example. M of t equals 2 times cosine of 2 pi 2t is applied to a switching modulator in which the rectangular pulse train has a height of 1 volt, frequency of 20 Hz, and a duty cycle of 1/2. If we want to look at the signal in terms of frequency, we'll have M of f equal, and then we're going to take the Fourier transform of M of t. When taking the Fourier transform of a cosine, we look at the amplitude, which is 2, and we take half of that, which is 1. Multiply that to delta of f minus, and then we look at the frequency, which is 2 Hz, plus 1 times delta of f plus 2 Hz. And then since the amplitude is 1, we can just write it as this. So on the frequency spectrum, we're going to have spikes of amplitude of 1 at 2 Hz and negative 2 Hz. Next, we'll have the rectangular pulse train, which I'll draw out. Alright, so it has a height of 1 volt. And since the duty cycle is 1/2, it is precisely a square wave. For rectangular waves, the exponential Fourier coefficients P of n equals AD sinc of ND. Sometimes you'll see H be used instead of A. That's just the height of the pulse train. D is the duty cycle, and N is the harmonic number. So in this case, we'd have P sub n equal 1/2 times sinc of n over 2. So writing out P of f, we'll have the summation from n equals negative infinity to infinity of 1/2 times sinc of n over 2 times delta of f minus the frequency. The frequency of the square wave is 20 Hz, so each harmonic n is a multiple of 20. And this part right here is P sub n. Next, I'm going to write out the table P sub n for height of 1 and duty cycle 1/2. For harmonic n equals 0, this is the DC offset of the pulse train. So since the minimum is 0 and the maximum is 1, the midline is at 1/2. For all other harmonics, you can find P sub n by plugging in for values of n in the sinc function. Since in this example the duty cycle is 1/2, every second harmonic, P sub n would be 0. So to start putting together P of f, we're going to start summing this for different values of n. So starting with n equals 0, we'll have P sub 0. Next we multiply that with delta of f minus n times 20. Since n is 0, we'll just have f minus 0, or just f. For n equals negative 1, we're going to have P sub negative 1, which is 1 over pi, times delta of f minus n, which is negative 1, times 20. This would just be f plus 20. For n equals 1, we have 1 over pi times delta of f minus 1 times 20, or just f minus 20. And then we can continue this for some of the other harmonics. Now that we have some harmonics, we can write P of f as follows. So the frequency spectrum of P of f is as follows. At V1 of t, when we multiply the message signal and the pulse train in the time domain, we'll get something that looks like this. And in terms of frequency, we're going to have V1 of f equals the summation from n equals negative infinity to infinity of half times sinc of n over 2 times m of f minus n times f sub c. V1 of f is the convolution of m of f and p of f. And we will have the following. Next, we will do the same process as before, where we plug in different values of n to get the summation for V1 of f. And then V1 of f can be written as follows. And then its frequency spectrum from n equals -3 to n equals 3 looks something like this. And then finally, V0 is the DSB-SC modulated signal. DSB-SC stands for Double-Sideband Suppressed Carrier. So on the spectrum, we want to keep these impulses. These are the sidebands, and we want to attenuate everything else, including the carrier. A bandpass filter is used to keep these spikes. So this is what V0 of f looks like. In the time domain, V0 of t, that can be used by taking the inverse Fourier transform of the above, or you can find the expression by just taking a look at the frequency spectrum and noticing the spikes. There is a cosine with a frequency of 18 Hz added with another cosine of 22 Hz. And then going back from frequency to time, we're going to double the amplitude. And then using Desmos, this is what the shape of the graph looks like.